Hello, my name is Elsa Cox, and for the past 2 years, I have been working in Notre Dame's Chemical and Biomolecular Engineering department on how to optimize water purification using membrane technology. And I'm currently a senior at Trinity School of Greenlaw. So to provide some context for my project, a large portion of the world's energy is actually used to make water safe for human consumption, but we still have a water accessibility crisis. Current technology is often either too energy inefficient to be practical in many regions, or is simply not effective in cleaning the water. Membrane technology is being investigated widely as a solution to these problems. Membranes, or microporous thin films, are thin sheets of chemically produced polymer with the structure of nanoscopic pores. By changing the chemical balance, the structure can be molded to fit certain applications, such as water purification. So how do membranes work? Well, I have here prepared a diagram that should help you visualize the mechanics of membranes. So on the left of your screen, we have what I'm calling a cross-sectional diagram of our membrane. Those blue arrows that are going through it are supposed to depict the current of the water. So the water will all be trying to flow through the membrane according to that current. On the right is the surface level view of the membrane, so like the top-down view. It's not really exciting now, but let's introduce some particles. So let's say we have some larger purple particles and some smaller green particles in our water supply. Right now, as you can see, our membrane is totally solid. This gray color that you see is going to depict the copolymer matrix, which gives our membranes substance. None of our particles can pass through that solid. So even though the current is trying to push them through it, they just can't get through. Of course, our membranes don't actually look like this. Ours are semi-porous. So here you can see that there are some pores in the polymer matrix. This allows our particles to pass from one side of the membrane to the next as the current directs it. Now, the way I currently have it set up, all of our particles are able to pass through the membrane. But in water purification, this is often not the case. We want to recover the clean water and exclude all the pollutants and dangerous heavy metal ions that can contaminate the water and make it unsafe for human consumption. Luckily, membranes allow us to be size selective. So let's say we only want the green particles to come through and that the purple particles are dangerous contaminants. Using different chemical formulas and processes for synthesizing our membranes, we can alter the pore size to only let the smaller green particles through and filter out the larger purple contaminants. In many ways, this system can sound just like the filters we encounter in our daily lives, like the typical Brita water pitcher filter. The difference is that while Brita is great at eliminating large contaminants like dirt and grime, our membranes are selective at the nanoscale, so we can eliminate much smaller pollutants. So all of that explanation of how membranes work kind of begs the question as to why these membranes could make an improvement on our current technology. If you look at the bottom of this diagram, written in the purple boxes are our current water purification technologies. The most selective processes are at the left, and the most unselective, most easy to produce are at the right. And in black, above all of them, are the sort of things that they are capable of filtering out of our water supply. So all of these processes described in this image, save particulate filtration, actually do use membranes to some degree, but they normally use large amounts of pressure to force water through increasingly selective systems to increase specificity. This use of pressure can take up quite massive amounts of energy, which may not be sustainable in many areas. The project I've been working on is attempting to combine the efficacy of processes like reverse osmosis, all while using less energy and making the overall process more efficient. This lowering of the energy barrier required to provide safe water will also allow people to gain access to clean water. So that now brings me to the project to my project in particular. For the past 2 years, I have worked with Dr. William Phillip and his graduate students at the University of Notre Dame's Laboratory for Water Purification and Advanced Transport Engineering Research, or the Water Lab, which seeks to develop next-generation membranes that are capable of extremely targeted chemical separations for advanced applications. This is filtration at the nanoscale. So instead of just forcing things through with lots and lots of pressure, we can become more targeted in our approach and use less energy. Specifically, the lab has been working with a specific type of copolymer called polyvinylidene difluoride, after which I'm going to refer to as PVDF. This project is quite expansive and has multiple labs working on different elements of the project. It works on everything from analyzing, scanning electron micrographs to trying to produce membranes with inkjet printers. So, and then this picture on the screen is just showing some scintillation vials that I worked with during the course of my project. So kind of hinting at things to come. So what does my work on the project really entail? And as it turns out, it entails a lot. Due to the COVID-19 pandemic, my work has had to adapt several times over the years, which has made it a bit difficult to explain all of my work with a single overarching hypothesis. But the general aim has remained the same. I have been working to establish some key relationships between the actual structure of the membranes and how they behave on the macro scale. I have endeavored to achieve this aim in the following ways. In the lab, I worked to determine physical characteristics of PVDF triethylphosphate membranes by synthesizing and then testing them. And then while I was at home over the summer, I worked to analyze my results and establish a process to analyze electron micrographs. And then finally, this school year, I have worked on simulating models at the macro scale. And I'm hoping to, at the end, sort of tie all of my work together. So let's start with what I did at the lab before COVID-19. I worked quite extensively to determine the cloud point of the membranes, which I synthesized of PVDF copolymer and triethyl phosphate. At the time of mixing these solutions, they were just a liquid solution, which you can see in these bottom photos. And so over the course of several months, I added in water, isopropyl alcohol, or a mixture of both, which you can see me doing in that first picture. And then I added those water or isopropyl alcohol until I reached the cloud point, when the once clear liquid develops an unmistakable cloudiness, which is showed in that third picture. This cloudiness indicates that my solution has phase separated. So a significant enough portion of the solution has bonded with the water and isopropyl alcohol that it has become partly a solid. Since membranes are a form of plastics and therefore solid, that's exactly what I wanted to see. I wanted to determine whether pure water, pure isopropyl alcohol, or a mix of both would most quickly and effectively plasticize my solutions. Ultimately, I determined that a 30% water and 70% isopropyl alcohol mixture was the most effective and efficient, and I was ready to formulate full membranes. So that's what I did. Once I finished taking the cloud point of measurements, I moved on to applying my results. I cast, which is our term for creating, quite a few membranes while in the lab. Using the data I found with the cloud point measurements, I was able to create dozens of small membranes that I could test to determine certain properties of the PVDF triethyl phosphate structures. So the tests I ran were wide-ranging and varied, and each gave me a unique insight into the structure of my membranes. I took permeability measurements and found how greater percentages of PVDF in the membrane affected the rate at which liquid could flow through the membrane. This in turn gave me insight into the structure of the membranes themselves. Since the slower the liquid passes through the membrane, the less or the smaller the pores themselves are. I also determined how pH affected the permeability of the membranes. I took viscosity and rheometry measurements on these membranes as well to determine the flow and durability of the liquid component of the membranes. And finally, I was able to have micrographs taken of the membranes I created. So in the pictures below, you can see all of what I've just discussed. First, you can see me casting those first membranes. Secondly, punching those membranes out into small circular pieces so I could put them in the third picture, which is depicting the device for taking permeability measurements. And then finally, you can see the scanning electron micrograph of one of my membranes that I took in the lab. So those electron micrographs actually bring me to the first major change in direction that my research had to endure. Once the pandemic hit, I could no longer work in the lab, so my work shifted online. I spent time analyzing all of my previous measurements at first, but I ran into a problem when I reached my SEM, my scanning electron micrographs. The micrographs are simply pictures. Micrographs are basically just like pictures of the membrane taken by an extremely sensitive instrument, but the picture itself has very little statistical significance, since there wasn't really a way to quantify all the bumps and holes that show up on the camera. These bumps and holes are really important because they are the pores that I talked about when I was explaining membranes. They're the things that make up the structure of the membrane itself. We want to know the membrane structure so we can optimize it for our process. You can get a good idea of this structure using the permeability, viscosity, and rheometry measurements because those all measure very direct characteristics of the structure. But without a way to statistically analyze the micrographs, you can't really know what your average pore size is. Presented with this problem, I worked throughout the summer to create a process that analyzes these images with statistical significance. I used a combination of Matlab, ImageJ, and Excel. By the end of the summer, I was actually able to analyze several sets of micrographs of my own and from those around the lab, and it showed that my analyses aligned fairly closely with what had previously been inferred about the structure through permeability measurements. This was really exciting, and it allowed me to give some new insight into other projects in the lab. I worked with one group in particular who were looking at how pore size variability impacted some of their previous calculations, which described how flux impacted selectivity of membranes. I analyzed their membranes using my new process and was able to show them how controlled our experimentally created membranes pore sizes actually were. This grounded their calculations in the reality of the lab, and they were able to adjust their models to more accurately predict the membrane's behavior. These pictures below are an example from that collaboration. And you can see that even the most precise membranes that we had available to us, those that were laser cut, still have a fairly wide pore size distribution, which does change how it does make a difference in going from the mathematical calculations to actually applying it to the lab experimentally. So then after the summer wrapped up, my focus on the project shifted once again. Since September in 2020, I have now been working almost exclusively in Matlab to simulate how certain factors at the model level can affect the recovery and selectivity of water in solutes. These two diagrams below show the systems that I have been working on. So there's the co-current system, which filters water by moving both the feed solution and the permeate solution in the same direction over a semi-permeable membrane, which is that black dashed line that separates the blue feed solution from the red permeate solution. So yeah, they were both moving in together in the same direction as the current, which is why they are co-current. This is in contrast to the counter-current system, where the permeate, the red solution, is actually going in an opposite direction as the feed solution. And so we want to know how those differences in systems affect them, and if possible, which is the most optimal way to to conduct our models so we can really optimize our efforts. So for a while now, I have been primarily focused on the co-current model. to show how changes in velocity and initial concentration affect plots of recovery, selectivity, and individual concentrations. The purpose of these simulations is to demonstrate the limitations of our process, because so much of it does depend on size differences, and there are lots of molecules that are roughly the same size. Using my plots, I believe I can determine what velocities allow for the most selectivity in size without sacrificing recovery rates, because we want lots of recovery of clean water and a lot of selectivity to make sure that that water is actually clean. And now I'm actually currently working on creating a countercurrent model in Matlab to determine which configuration is optimal for our desired factors by comparing them to the co-current models that I've already collected. And so then these pictures here are showing how the concentrations in the feed and the permeate and their concentration difference changes the function of position. So change as they go through the system and make contact with that semi-permeable membrane, and they pass through it. And so as you can see, they go through very quickly, and the velocity does make a very direct difference on at what point do they reach that equilibrium, at what point both the concentrations in the red and the blue come together. And then on the right, you can see the recovery and the selectivity also plotted against position. And again, those factors of initial concentration and velocity do still make a difference. And so I'm looking closely at how we can best optimize those. So that is my project. As I mentioned, I've been working on this for 2 years, and so I've done a lot. And if you are at all as even like slightly interested in this project, I would highly recommend going to this website to check out more publications that came out of my lab, so you can get a little better insight into what I've been up to, because it's a really fascinating project and I've loved being a part of it over the past 2 years. So with that, and these are just some more pictures of my work at the lab, I want to open it up to any questions that anyone might have.
Well, before I even ask a question, I just want to say that was great presentation. I think I learned so much from you, Elsa. Looking at all this research, what do you think you could implement this in maybe 10 years? Do you think you could maybe fix the water crisis, or?
Yeah, that's a great question. So I know that the hope for this project is specifically is to sort of commercialize this purification system to lower the energy and cost barriers across the world if possible. I mean, the hope is that this is not only lowers our effect on the planet by reducing the amount of energy required for something as crucial as clean water, but like also that we can help to create more equity for low-income cities and towns that may not yet have a healthy water supply. But again, this is a long-term goal, and in this field, we tend to sort of reach for the moon. We want to do as much as we can, but it is a long-term process, and a lot of work still needs to be done. So within the next 30 years, I don't know what we could really been looking at this, even within the next 5 to 10. There's a lot of energy in this field because it's still pretty new in terms of like fields for sciences. And so there's a lot of energy into it across the country and across the world. So there could very well be really incredible and impactful strides that we're looking at. But so that we can get to a certain point where this is implemented in a really beneficial way. But yeah, that's going to take quite a bit of time. There's still a lot of work that has to be done, but it feels good to be moving in that sort of direction on this project.
Thank you, Elsa.
Yes, thank you, Maria. Thank you for asking those questions.